Hello, this lecture is Subspaces. This is a continuation on the subject of vector spaces, and we're going to review some properties of certain subsets of vector space that inherit the 10 properties of the definition of a vector space together with the operations that define the vector space. So suppose we have two sets, one of them contained inside the other one, and they are both vector spaces with both identical operations. So let's recall that a so-called vector space has two operations. One of them is the so-called addition. That is an operation in which you can add elements, members of this set. This addition for vectors in CM or for matrices is something very standard. We're very used to add up column vectors or add up rectangles. But vector spaces, as we know by now, are much more theoretical, much more abstract sets. So therefore, we could define in a much more abstract sense the operation we call addition and the operation we call scalar multiplication with very specific rules as to what these operations are. The thing is that even with a very special or unusual definition of addition or scalar multiplication, we here refer to two subsets, two sets, V and W. They are considered vector spaces, and they have identical definitions of these operations. And we are going to consider W being inside or being contained in V. And if that is the case, then we would say that W is a subset, but because both of them are vector spaces with the same operations, then we name that set W. We baptize that set with another name, which is called subspace. Okay. So now we learn a very useful theorem to classify a subspace. Remember that the hard work that is involved in classifying a set as a vector space is mostly due to the fact that there are two operations and there are 5 properties associated with each operation. In total, there are 10 properties, and if we have to justify or really prove from scratch that this given set is a vector space, we have to verify every single one of those 10 properties. Okay, this theorem is going to give us a way of classifying a set, really a subset, as a subspace, and in that classification, what's happening is that we're ruling this set really is a vector space by inheriting the properties of the bigger setting, which this candidate is contained. So this is the theorem that we will use to do so. We suppose that we have a vector space that is denoted with the letter V, and the W is a subset of V. We suppose that both V and W have the same operations, addition. This would be addition, okay, and scalar multiplication, right? So we suppose that both of them have these operations defined in the same way. And so we're going to classify W as a subspace if and only if. This theorem is very useful. It's an if and only if, so it has both directions. These 3 conditions are satisfied. First, we have to argue that the candidate is a non-empty set. Second, we would say we have to verify that if 2 arbitrary elements of this candidate W are selected, and if they are passed on as arguments of the addition operation, then the output of the addition, this output x plus y, is indeed a member or an element of W. And well, if I may, by going back, this is no other thing that closure. Okay, we would say that this subset W is closed under addition. So this is additive closure, if you will. Additive closure under the addition operation. And then if you consider a complex number and then an arbitrary element of the member, an arbitrary member of the candidate set, then use that complex number to compute the so-called scalar multiplication, and you find that that scalar multiplication is also inside. So this both of these properties, 1 and 2, are referring to what we know as closure, right? The property of being closed under the operations. So suppose that we consider now the set P sub 4 as the vector space of polynomials of degree 4. In general, these polynomials, if we remember, for example, a parabola is a curve that looks like this. You may think of this curve as x squared, right? And in general, a parabola would be described as with coefficients, say a x squared plus b x plus c, right? So if you think of a parabola with this type of shape, there is only one little valley here, right? So these are polynomials of degree 4. They may have a similar shape. A polynomial of degree 4 may look like this. An important thing here is that when we refer to the intersections of this curve with the horizontal axis, those intersections are the so-called, if this graph is the graph of if this graph is the graph of a polynomial, say p of x, then these points right here are precisely the points at which we would say that p is equal to 0. All right. Okay. So we can call these points specific names. I don't know, like maybe x1, and this could be x2, and this could be x3, and this could be x4. So the idea being is that at those values, the value at each of those values of x, the value of the polynomial x1, p, the polynomial evaluated x1, is equal to 0, and p evaluated x2 is also equal to 0, and p evaluated x3 and then x4. So each of these values is called a root, okay? A root of the polynomial. They also typically are referred as zeros. So these are also known as zeros of the polynomial. Okay, so and in general, we would say if it's a polynomial degree 4 that it has an expression that has powers x4, x3, x2, x1, and x0, and then it has coefficients. So one way of writing a polynomial degree 4 is this expression that appears here. So let's now consider a subset in this family P sub 4, polynomials of degree 4, which is defined in the following way. It says that W is P of x. That means W is a set of polynomials such that those are polynomials of degree 4, but they are evaluated at 2. They are equal to 0. This means that W is the set of polynomials of degree 4 with 2 as a root. All those polynomials of degree 4 that have the number x equals 2 as a 0, or x equals 2 as a root of the polynomial. And so what follows now is to explore whether or not this set, which is a subset, this set W is a subset of the vector space of polynomials of degree 4. So we can write it like that, or we can just say W is contained in P sub 4. And so what we need to address is whether or not W is a subspace. We know that P sub 4 is a vector space. We know that W is a subset, so is this a subspace by means of applying this theorem? And so first, let's address if it's non-empty. It is possible to find at least one member of W. That member is x equals 2. You may think this is a little bit like committing fraud or something, but so, well, maybe it is. Here is x minus 2, and it turns out that you can think of this as 0x4 plus 0x3 plus 0x squared plus 1x minus 2. So this would be 1x minus 2 x0. And so this indeed is a member of W, which is also contained in P sub 4, right? And so clearly, if you evaluate x minus 2 at 0, so if you think of I'm going to use another letter here. Maybe I say L of x is x minus 2. And so if we evaluate L at 2, we have 2 minus 2, which is 0. So that means that this expression x minus 2 indeed is a member of W. And that we used to argue that W is not an empty set. In other words, W is non-empty. The answer here is yes. Right? Well, we had that there. Now, what about the closure and their, I apologize, I had misspelled closure probably in one of my previous slides. So, what about closure and their addition? So, if you consider two polynomials, arbitrary members of the set W, and now we consider the sum of these polynomials. This goes back to the definition of adding functions or adding polynomials. Consider what happens exactly at the number 2 when you evaluate the sum at number 2. So P plus Q evaluated at 2 by rules of adding polynomials in P sub 4 becomes P of 2 plus Q of 2. Each of those has a value of 0, which means that 0 plus 0 is 0. Therefore, the new polynomial P plus Q evaluated at 2 equals 0, and that's exactly what we need to argue, that this new polynomial that results from adding P and Q to arbitrary members of W using the same definition of addition of polynomials in the vector space P4, that new polynomial has also 2 as a root, or 2 is also a 0 of that new polynomial P plus Q. Therefore, this establishes that W is closed under addition. Okay, and last but not least, what about scalar multiplication? So if we consider an arbitrary complex number, an arbitrary member of W, we know that because that polynomial is a member of W, has 2 as a root, and we now need to establish what happens to the scalar multiplication alpha times P. Well, alpha P evaluated at 2 is the scalar multiplied by the polynomial evaluated at 2. We know that P of 2 equals 0. This is precisely what we have, what we're using there. P of 2 is 0, therefore alpha times 0 is 0, and this establishes that indeed the scalar multiplication is closed. So the three conditions of the theorem are satisfied, and therefore we would say that we would rule here that W is a subspace. So W is a subspace of P sub 4.